Okay, I'm audible now, I think. Good, okay. So thank you for the kind introduction, and I'm very happy to be here. It's lovely as always. About my talk, so this will be a talk in probability, and but the problem that I will discuss is really very much motivated by applications, but there won't be any applications in this talk, okay? So really, the reason, so what I'm interested in is the stability of Markov processes, ergodicity and rates of convergence. And this is a problem that we are all familiar with, in the sense that anybody who's ever run NCMC knows that you need to know whether the chain has converged or not when you're sampling, right? So this is exactly the type of problem that I will be looking at here. The point is that I will, of course, look at continuous time context, because the theory we develop in continuous time, but these things also apply in discrete time, okay? So I'll describe the models and what we're looking at. Okay, so I should say this is joint work with Miha Brešar, who was my PhD student and is now a postdoc at Warwick. Okay. So, right. A canonical sort of model, or a starting point, is a diffusion process of, can you see the cursor? Yes, you can. Okay, so I can use that. Is a diffusion of this type on RD. And we are interested in diffusions that are sort of stable, that converge to a stationary measure pi. Now, of course, pi is not given explicitly potentially, but more precisely, we're interested in the case when this convergence is not geometric, it's not exponential, okay, when there's no spectral gap in the generator of this process, okay? So this means that stationary measure will typically have heavy tails, and the convergence will also be polynomial, okay? So now the starting point is this sort of process. And okay, so there are some conditions here. So this is a large class of processes in this example. And you see the key thing to note is that this parameter L sits between 0 and 2. And so what that means is that this drift, which has to be pushing, when the process is far away, it has to be pushing it in, right? But it's pushing it in back towards the origin, towards the sort of the mass, the center of the mass of the distribution, in a sublinear way. You see, L is strictly smaller than 2, okay? So what this will do is it will make the stationary measure heavy-tailed and the convergence potentially much, much slower, okay? Now, of course, the volatility of the process also has to sort of correspond to this kind of behavior. And here you see when L is positive, this volatility here is going to be unbounded. Okay, the volatility is going to be unbounded. And indeed, this volatility needs to be unbounded for the process to be ergodic. So I wrote here on this board, but I checked later, it's not really visible from the back, right? So the thing to keep in mind, so what we're comparing with is the Ornstein-Uhlenbeck process, okay? So the Ornstein-Uhlenbeck process is not like this. So the Ornstein-Uhlenbeck process has a linear drift pushing in and has a constant volatility, okay? And this guy converges very, very fast, converges geometrically to a very thin tail distribution. In fact, geometric convergence is even exhibited by this other process that I wrote here, which you probably can't see from far back, but the drift here is bounded, okay? It's got a bounded drift pushing in and constant volatility. Even this guy is geometrically convergent to a distribution which will have exponential tails. Now here, a model like this will not have, will have a stationary measure and the process will converge to it, but the tails of this stationary measure are indeed heavy, okay? And there is an important paper by Ford and Roberts from 2005 where they actually proved that, you see, what you're interested in any stochastic system, being physics or computational statistics or whatever you're doing, you want to know how far you are from the stationary measure, right? How quickly that distance decays. And the distance you typically measure in total variation. So they proved that this thing decays, the total variation between the marginal of the process and the limit decays decays polynomially slowly, okay? Where this MC is just some function, explicit function of these constants, gamma, beta, and alpha in this model, okay? So you see this gamma here is just to give some sort of concrete context. If this volatility matrix here was a scalar times the identity, this gamma would be just the dimension of the space. Okay, that's what it would be. And this beta is something that also sort of features in it features in this critical exponent MC. Okay? So this is good. This was a really big step forward because geometric convergence was the only thing that was sort of known how to establish in this context. But of course, when you write models down in statistics and elsewhere, heavy tails arise, even though you don't put any heavy tails in the model. Like for example here, right? I just write the diffusion down. I drive it with Brownian motion. I sort of curve the growth of the drift, and that's what happens. I get heavy tail distribution pi, and I get this slower convergence. But of course, this could be just a bad bound, right? So this bound is really very slow. Maybe this converges geometrically, and just the proof is not good, right? This is somehow the point. So this was our starting point, right? So is there any lower bound that will sort of match the same rate so that you actually know what the rate is? This is just an upper. So often people talk about rates, but really what they get is upper bounds on rates, okay? So what you want to know whether this is actually the rate or whether this may be exponentially or some other way convergent. Okay? Right. Okay, upper bound, lower bound. So now, because I will start by giving you a one slide primer of mine and Tweedy theory in continuous time. Okay, so this is something to keep in mind. So to explain how the upper bound was proved, and then I will contrast this or sort of add to that by explaining our results, our drift conditions, okay, that give you the lower bounds. Okay, so this mine and Tweedy theory is this so convergence of Markov chains. So Eric was here, Eric Moulin was here. Also, he's an expert, and he in fact has the latest book on the convergence of Markov chains in this sort of area. And this is something that sort of works in astonishing generality. In other words, you don't need to assume any SDE structure, no Brownian drivers. It's just some sort of general assumptions on the process. So you want your process to be reducible, which in plain language means that it goes everywhere, okay? As time goes to infinity, the process will not leave some patches of space not visited. And you can do it on a general locally compact space X, okay? And then, so this is this idea of Lyapunov functions, right? So this is with the cornerstone, right? So what do? You have this complicated space, a complicated process, and then if you can find a function V, like that V, that maps this complicated space into a much simpler space, okay, such that, and then also find a function phi, which is increasing and concave. So it's a function that's increasing and concave, but it's a scalar function, and such that this process here is a supermartingale. Supermartingale means that it converges, it's in expectation, it decreases, okay? If this is supermartingale, then the process will be Harris recurrent with invariant pi. So it just means that the process will have some good properties and will have invariant measure pi. And in fact, this function phi composed with V will be will have finite expectation with respect to this invariant measure pi. You see, note here, I'm given the Markov process X, which is given somehow by, of course, always given by its infinitesimal characteristics. I described the process, how it behaves locally. But pi, of course, is a consequence, is something complicated and completely non-explicit because it's something that depends on the entirety of the process, okay? So this statement here, the first statement, already very interesting because it simply says, okay, if I can check that this guy is a supermartingale, which I can do from the characteristics of the process, right? So for example, if this is an Ito diffusion X, then I will just use Ito's formula. I need to cook up the function V, and then I use Ito's formula, and I see, if the drift outside of compact sets is really negative everywhere on the state space, then this will be a supermartingale, generically, but typically true. And then if that's the case, then I immediately know that this function is integrable with respect to pi. Okay? And this tells me, by Markov inequality, immediately an upper bound on the tail decay of pi. Okay? So this is somehow the first step. Is that clear? See what I mean? Okay. And then once you know that this function is integrable with respect to pi, what you can do is you can then obtain an upper bound on the distance between pi and px. Okay? So the marginal at time t. So this looks a bit complicated, so let's try to unpack it a little bit. But it's really not. I mean, so you see, in this case, classical Mind-Tweedy theory, convergence of Markov chains, in the geometrically convergent case, this phi would simply be the identity, or some multiple of the identity, okay? So that is a concave function. And if this is a multiple of the identity, let's say that this phi of s is equal to s, then this function h phi is going to be just log u, right? Because it's an integral of 1 over s. Okay, so now look at this log u, and you here I need to take the inverse of log u. Well, that's going to be e to the t, right? So you see, this tells me, this bound tells me, and phi again is the identity. So this bound tells me if phi is a multiple of an identity, then this bound is in fact a geometric bound. Okay, so this is how this theory starts. And then I was chatting to Eric whenever it was, Friday maybe, and he told me, I was the first guy actually who wrote down this general drift condition phi, okay, with this concave, increasing and concave function. Okay, so this goes back to one of his papers on independent sampler, which is a very, very special kind of thing for in the sort of MCMC context. Okay, but of course this sort of holds much more generally, and this reference here is mine and Tweedy, which did it for the first time already in the early 90s for continuous time. And then this is the paper that somehow motivated, or we used for much of the stuff that sort of goes in here for the upper bound. Okay, this is Duke, For, and Quillin in 09, and these are Martin Heirer's notes, which are contain all this theory, but also contain a crucial idea that I will try to describe at the end that allows us to get lower bounds with the theory that we're going to explore. Okay, you see, so that's that was the state of the art before we started. So this kind of thing is very general and very, very used, right? So this paper, mine and Tweedy paper, has thousands of citations. I mean, for a maths paper, this is quite astonishing. And the reason for this is precisely its generality, right? Here, I don't assume anything. All I need to do is have this function v. So I should say, what is this v, right? So how to think about these Lyapunov functions? So you should think of them as, so this maps my state space, a complicated state space, to r plus, or 1 to infinity. So it has, the sub-level sets are going to be compact. So v is some sort of increasing function, okay? So these sub-level sets, so v smaller than something, it's a compact set, and I get an exhaustion of the space. And the growth rate and the shape of these contours that are given by v, this is somehow dependent on the process, okay? And this dependence is really contained in this supermartingale condition, somehow expressed in the supermartingale condition. Okay. So, but however, this tells you an upper bound, but you have no clue whether this upper bound is any good or not. Maybe this quantity here is many orders of magnitude smaller, right? If you get the wrong Lyapunov function, this will actually be the case. And up to now, there has been no way of checking whether the given Lyapunov function is any good or not. And this is precisely what our lower bounds will do. Okay, right. Okay, so I'll go a little, I mean, I've got lots of slides and I've got lots to say. I want to talk about the proof and stuff like that. But if we don't get there, I don't mind too much, right? I mean, I just want to convey somehow the ideas and I show you the examples, and then we'll see how things work. Okay, right. So now we have this problem. The problem is clear. And the first thing I need to do is I need to explain how, what our drift conditions are that are going to give us our lower bounds. Okay. So lower bounds, of course, are harder than upper bounds. The reason there are many ways to look at this, right? But somehow, if you think about an algorithm, a stochastic algorithm, right? So bounding how much time it will take is easier than saying a priori at least how much time it has to take in any circumstance. Okay? So of necessity, we will need new Lyapunov drift conditions, and there will be two in this case, and I will just describe them now. So we start with the Lyapunov function, okay? And now there are two conditions, okay? There are two drift conditions which somehow the first one feels a little bit similar to the previous one, right? But so the key idea behind all this is to look at 1 over v of x rather than looking at v of x. And you see, somehow this is not completely insane because you want a lower bound on something. So an upper bound on 1 over that something is a lower bound on something, okay? Now the function v is growing, right? That's how it looks, it's growing. Now 1 over v, being a super martingale on its own right, is not necessarily going to be the case, right? I need to be able to correct it by some positive thing. So subtract some positive thing, you see, because this minus here, this makes it more of a super martingale. 1 over v is not going to be a super martingale, but if I can find a phi such that this thing is a super martingale, you see, I'm sort of consistently ignoring this last term because this last term is somehow not of great fundamental importance because this is something that is only kicking in when the process is in the bulk of the distribution. I'm interested in excursions away from some compact set, okay? So I'm thinking, how long is it going to take to come back? That's what drives the tail decay and the speed of convergence in these sort of heavy tail situations. Okay. So let's forget this for now. And so this guy needs to be a super martingale, but for this function phi, it needs to be of a special form, okay? This function phi is a function from 0 to 1, and it actually at 0 will have limit 0, but it needs to satisfy this condition. So when r goes to infinity, this function goes to 0 faster than r goes to infinity, okay? So this is something that comes out of the proof. This is sort of necessary. So that's the first condition. So this is super martingale condition. And then the second condition is something that has to do with exit probabilities, okay? So I'm now, you see, I take my process, I don't know what to do with it. It's a very high dimensional, complicated thing. I map it into a scalar thing, which is v of x. And then I worry about this process v of x sort of exiting below, you see, v of x starts between L and some larger level R, okay? So this time is the time I start the process v of x at v of little x, and then I wonder about the probability that I exit the interval above rather than below. And I need a lower bound on that probability, okay? So this lower bound is, I assume that there exists a submultiplicative increasing function psi such that this probability is lower bounded by this, okay? So this is a somehow probabilistically a condition which is easy to state, but when you tell a user of Markov chains for simulation, this kind of thing, they immediately say, okay, so the first condition is a super martingale condition. That's great because I can just use the local characteristics to compute it, right? To check it. This thing looks very complicated. In fact, it is not, but it has, under a mild restriction, also a drift condition representation, which is sort of written here, okay? So you see, now if I take this psi composed with v to be a submartingale, if this is a submartingale, now what is a submartingale? You see, psi is increasing, v is increasing. Submartingale is something that's increasing on average. If this is a submartingale, again, I'm consistently ignoring this bit, as I say, because I'm interested in the behavior far out. Then actually this lower bound holds by a very simple argument that fits here at the bottom of this slide, okay? And I will now show you how that's done. Okay. You see, forget about this limit for a moment. And just look at this t. I fix t, and I take the minimum of these stopping times. This is the exit above, exit below, and time t. Now, this is a super martingale. It's a submartingale, this guy. So the expectation for a fixed t is surely greater than the value at the starting. Okay. Now, this holds for all t, so I take a limit. But this variable is going to be bounded. So why is it going to be bounded? I mean, this is why this condition 2 is not written in terms of a submartingale, which I would have liked to do, because here I need to assume also that the jumps of this x are bounded, okay? Because, okay, so here is one place where I can use this, right? Because if the jumps of x are bounded, then, you know, the overshoot, this means that when I exit above at a large level r, I will be no further than r plus d, obviously, right? And if I exit below, well, I'm below, but that doesn't matter because all these functions are sort of increasing. So the point that I'm trying to make is that this limit, if this is bounded, I use dominated convergence, and this limit is equal to this expectation, right? But this expectation is somehow, again, a silly expectation. There's only two things that can happen. I exit above or I exit below, right? So if I exit above, that's this guy, and then the value of this function is really psi of the level that I've crossed plus the maximal possible jump that I've had. Like, for example, the process could be continuous and d would be 0. I would have nothing to do. So that's one side. And the other side, there is a probability here, which I bounded above by 1, which is that I exit below. Right? And that probability is also going to be bounded by the value of the process after I've exited below. But that value is smaller than psi of L, because psi is increasing, right? So I look at the lower bound of my interval, and then I'll be somewhere below, but psi is an increasing function, so I take the largest possible value, okay? And then I do this, and that's okay, because now I just, out of this simple thing, I get a lower bound on this exit above. Okay? How? Well, this is this constant CL, which depends on this lower bound L. And I use, of course, that's why I assumed here that this psi is submultiplicative, okay? It has to be submultiplicative. So submultiplicative means something like this. And you see this psi of d is sort of this bound on the jumps, okay? So there's, again, to recap, I've got two drift conditions. One is a super martingale drift condition, and one is a submartingale drift condition, essentially, okay? And now if I do that, let's say that this assumption holds, then I dream up this function, this funny looking function, okay? It consists of r times psi of 1 over r, phi times 1 over r times psi, right? So these two functions featured in this, my L drift condition. And this function will end up being a lower bound or play a key role in the lower bounds in this theorem, right? So this is our main theorem. And what does this theorem say? Well, it says that, you see, in this context, pi has lower bound, which is given by 1 over this L of r, right? Okay, so now this is making me a little bit funny. You see immediately here that something non-trivial is going on, because you see here, I've got this term, r times phi 1 over r. And this term is assumed in my assumption, to go to 0, okay? This guy goes to 0. See, this guy goes to 0, and this guy will go to infinity. Of course, this r goes to infinity. Now, but this thing has to be a lower bound. So this thing, this L, has to go to infinity, of course, for this to be a sensible lower bound, okay? So it says that this guy, somehow, if the assumption is satisfied, this psi needs to beat this other function, right? But this is sort of not a priori clear at all. In any case, this is going to be a lower bound. And then from this lower bound, we can obtain an upper bound using this idea of higher. And for this to work, what you do is you need to get some control on the tail of the marginal distribution of the process at time t. And for that, you need upper bound control. And for this upper bound control, I will just bound the expectation and then use Markov inequality. Okay, so this is what happens. And so in order to, so there is this hyperparameter h. This is some function that I need to find. Typically, this function is simply going to be the identity. I take this expectation of the process at fixed time t, if there is some function little b that's sort of growing in t for fixed x, then this function can be used to obtain, okay, let me just show you, to obtain this lower bound, okay? So how do I obtain this lower bound? Well, I have this L, 1 over L, which is a lower bound on the tail of the stationary measure. And then I take any a, small a, which is decays not faster than this lower bound. So this little a is also a lower bound on the tail of the stationary measure. But it needs to decay fast enough so that it shouldn't decay too fast, because this r times a of r still needs to go to infinity. And if that's the case, I get this function which sort of lower bounds my total variation. Okay, so this somehow looks like a little bit crazy construction, right? You put these functions together. If you parse through this argument, you will see that this thing actually, the lower bound, of course, will go to 0. But it turns out that this lower bound is actually sharp in all the cases we tried it. Okay, so I will try to convince you of this by showing you now a number of examples. Okay, but before I show you the examples that will sort of answer this question, or this generic question that I posed earlier, if you have some polynomial or sub-exponential convergence, do you get a lower bound that is of the same rate? Okay. So before I can show you the examples, or before I show you the examples, I need to tell you how one in practice checks this assumption L. Okay, so this is something that you need to dream up this function, right? Phi, psi, and v. Okay. So this is what the next theorem is about. And of course, what's going to happen, right? We're going to work with the generator of the process, or this extended generator of the process. So what's an extended generator of the process? So it's some operator that has some domain, okay? And now, if my Lyapunov function, which I typically have because somebody else has already worked on the upper bounds for my problem, right? So I have a Lyapunov function, and I now to see if this Lyapunov function is good, if it gives sharp bounds. So I look at this 1 over v, and if that's in the domain, then then I can actually, what that means is that this process here is a local martingale for any starting point x. Okay, that's just the definition, a probabilistic way of saying what an extended generator is. Okay, so you see, this simply means that this a of applied to 1 over v is somehow the drift of this process, right? Because it's this plus some local martingale. Right? So the drift is contained here. So you see, all my drift conditions are therefore going to be transferred to some bounding this quantity. Okay, and this is what this theorem says. Essentially, it says, okay, so if this a of 1 over v is bounded by this function phi of 1 over v, where this function phi is such that satisfies these assumptions that I stated in this L drift condition 1, then the process indeed there is going to be a super martingale. Right? This is not surprising. Okay, this is not surprising. And similarly, if I look at this function psi of composed with v, that's my other, this L drift condition had 2 parts, right? So this psi, and this psi is in the domain, and is such that it is positive outside of a compact set. If it's positive, this means that the process psi of v of x has positive drift far up, right? So this is all I need for my submartingale condition to hold, okay? And if the submartingale condition holds and I have bounded jumps, say, then I'm done. So this is now a toolkit to use that theorem for lower bounds, okay? Of course, if the bounds are not, if the jumps are not bounded, you have to work a little bit harder to verify the second condition, right? And this is what we'll see when I look at some Levy-driven SDs that we can also, of course, treat here. Okay? How am I doing time-wise? What time did I start? I started like 10 past or half an hour. Okay, I've got half an hour still. Okay, good. Good. Okay? Ready for more? Okay, let's see. So now I give you some examples. I show you how to. You see, now we're armed, right? We're armed. We can tackle this problem. We're actually armed to the teeth. You see, we'll do quite well. So I go back to the problem that I started, which is this diffusion, right? And this diffusion under these assumptions has heavy-tailed stationary measure. This was proven by Ford and Roberts in 2005. And now we go And we apply that theorem with generators to to verify this assumption, the L drift condition assumption, right? So I need to dream up the function, right? So as I say, I mean, this function, the Lyapunov function is sort of known, and the scalar functions are also polynomial in nature. I will be able to verify these sort of inequalities outside of a compact set. And now that this, I can do it with these functions phi and psi, given here explicitly. See, they're not very complicated even. See, mind you, you see here, this model is really a very broad class of models, right? This is not, I don't specify these mu, sigma, and whatever it is, right? B, right? I just tell you how it behaves in the limit. That's all I say, right? If it has this kind of limiting behavior, it's such and such, right? And of course, this is somehow natural because you're thinking about long-time behavior of the process, stability of the process. It should be only what happens in the tails that matters, right? It shouldn't depend on what happens in locally, as long as you have some uniform ellipticity. Okay. And okay, so we do that. And then we just look at this function L, right? This is my lower bound function. I've got this phi and psi. Okay, I calculate this. This got this some log term, but because these guys are polynomials, this log term will disappear, and I get this kind of lower bound on the tail behavior of pi. You see, I have no clue what pi is. I don't even know what b and sigma are. I just know their asymptotic behavior. But then if they have that asymptotic behavior, this lower bound has to be polynomial of this order. You see, and again, this is explicit in terms of the coefficients. If you're wondering about this epsilon here, you see this epsilon is arbitrary. And it is exactly the consequence of the fact that I'm not working with mud model, because I don't know how long the process, I will decompose these ideas, go back to Dublin, right? So how do you study stability? You look at some small set, and then you look at excursions away from this small set, okay? And these excursions are approximately IID. That's the basic idea. But because I don't make assumptions on the model, I don't know how long the process spends in this small set. Maybe it's going to be slowed down a lot, maybe not. That's why these things have this, the rate here has to be a sort of polynomial. There's a perturbation in this polynomial lower bound. Right, okay, and then, what do I say? Right, so this is the same model. And you see, I had the second part of the theorem that sort of translates the lower bound on the tail of pi into a lower bound on the total variation. But in fact here, because, you know, I had in the title F variation, right, instead of total variation. So I just write here what F variation is. This is a notion that statisticians like a lot because it is stronger than F variation. You see, I take some positive function F that sort of grows, maybe some polynomial like here. And then, you see, if I took F to be constant equal to 1, I would get total variation. Okay, that's the point. So I allow this growth. And the reason why people like it is because it allows them, it makes sure if you converge in this norm, which is a very, very fine norm, then the moments up to this F will also converge, right? So that's somehow a natural thing. And this doesn't present much of a problem, right? In any case, we get this lower bound. This eta k depends on the model parameters. You know, this is M critical, which depends on alpha, beta, and gamma. And this L, which is here, right? And this k, if I take k equal to 0, as I was saying, I get total variation here, right? But so this k is of this type. Okay.
So
yes.
What's the upper bound in that case?
I will show you now in the next slide. Yeah, of course. Because this is right. It is exactly this. See, the upper bound is exactly the same. This is the point. You see, we do these crazy things, do some new stuff, and we get a lower bound, and then it matches this upper bound. So Fortin Roberts' actual result was good, right?
Tight.
Yeah. I like, and I definitely agree with you. Yes. Right. Okay. So that's that. Now, that class of models that I discussed in the previous slide is sort of interesting because it contains the sort of widely used Langevin diffusion case, right? If I take pi that has polynomial tails, like I take this pi like here, right? Some pi with polynomial tails, okay? And then I go and calculate this quantity. You see, if pi of x decays as 1 over x norm x to the alpha, for some alpha, then the drift will be exactly of this form. You see, because if I have polynomial tails, I have log of the tail, so it will be log of x to the minus alpha. That's minus alpha times log of x, okay, for large positive x. And then when I take the derivative or the gradient, I will just get 1 over x times minus alpha, right? So this is for the polynomially decaying case, right? And in this case, this is the case when this L, you see, this drift is immediately very weak. You see, this drift is pushing in, sigma is constant, but it's sort of vanishing, right? It's vanishing. Nevertheless, this diffusion will converge, and the known upper bound from Fortin-Roberts for this is this eta 0. You see here, you can see how the dimension features in this thing, right? So this dimension, as I was saying earlier, comes from this the trace of the identity, right? So this gamma is n here. So there's this, and our lower bound is exactly of the same order.
Epsilon is hiding some log terms, essentially.
So epsilon is arbitrary.
Yes, but it is there because of some log terms or what?
Oh, no. Epsilon is there because again, I only assume how pi behaves in the tails. I don't have any information about pi in compacts. So pi could have some really very regions where maybe some circular behavior is. So the process can spend a lot of time in the bulk, right? So that is asymptotically not going to drive the behavior, but it could deteriorate, right? So the reason why I can take here arbitrary epsilon is because that epsilon will be reflected in these constants, right? So I could make epsilon arbitrarily small, but then I'll have a bigger constant, because my point here is that this bound, this rate, holds for all time, right? This is somehow the point, right? Time 1 to infinity, okay? So that's the point. But so the point that I wanted to make here is that when you have heavy-tailed target, sometimes it is better to use a diffusion process. For example, here, this Langevin tempered diffusion, which has unbounded covariance structure, okay? Like here, it is not hard to check that this diffusion, you see, I introduced a new parameter, d, okay? And if I take d equals 0, I get this process. All right? And now I take this new d, which could be positive, and it's easy to see that the stationary measure for this x is pi, okay? That's easy to see. The volatility is going to be now unbounded, right? Because this guy, of course, when x goes far out, this goes to 0, right? It's unbounded volatility. So this is this fast martingale idea. You know, it's sort of time change Brownian motion by something that sort of moves faster, the clock goes faster. And then I will come back I'll come back to the compacts faster. Okay, so to sort of now I can actually justify this intuition by these theorems that I have given, because you see, this diffusion also sits in that Fortin-Roberts class. And now I do the same calculation. Okay, if I take this L will be something that's proportional to 2d times whatever the exponent is of this pi when x is big, okay? And if I can make this L very close to 2, I will get this rate of convergence for eta 0, not of this type, but of this type. And you see, when L is close to 2, 2 minus L is tiny. So this number is huge. So in other words, I fix a stationary measure that has heavy tails. I can find a diffusion that converges to it faster than the actual Langevin diffusion. So it's going to converge faster than any given polynomial rate. This is somehow the point that I'm trying to make here. And now, of course, I can make these statements because I know in each case what the rate actually is. See, if you just had upper bounds, you would not be able to say that, right? Because you would just have an upper bound here and you wouldn't know how slow this guy actually is. Here, an upper bound is good because an upper bound tells you that it converges very fast, right? You see, because I'm dividing by this polynomial, so I want the polynomial to grow as fast as it can, so I want to maximize this eta 0. And this L close to 2 will make this eta 0 very big, okay? Is that clear?
How much can one push it? Because, I mean, if one thinks of the standard equation, right? I mean, one can try to introduce sigma constant in the dB and some corresponding in the other. It's like a parameterization of time. I mean, here you do it stochastically.
Yes.
how much can you push it? I mean, is
Yes.
this just one mechanism, or you
Yes.
think that there's something more
Yes.
general?
Yes, yes. I think that this is generally an open problem. Okay, so here and it's sort of maybe context dependent also, right? So this is what I'm talking about, is somehow a tool to analyze all these things. We did not somehow try to, we just look at what people have done in terms of upper bounds and then provide lower bounds, try to see whether their upper bounds are good or not, right? This is somehow the point. But of course, what you're saying is, of course, very sensibly using this, because now these conditions also give you some intuition how the process behaves. So maybe they're useful for sort of constructing good ways of sampling. This is somehow the point. This is my motivation.
This is
my motivation. Yeah, exactly. But we didn't do this here, right? So, but definitely. Okay, so what am I doing now? So I've got 20 minutes roughly, right? Including questions. Okay. So you see, there's another class of diffusions, which is also liked by the French in particular, Eric Moulin included, which has these stretched exponential tails. Okay, so they're subexponential in that, so you've got e to the minus not x in the tail, but e to the minus x to some power alpha, where alpha is smaller than 1. Okay, alpha is smaller than 1. So, and in that case, you can express a large class of such diffusions. Will have sort of this stationary, what I'm trying to say is that this class of diffusions will have a stationary measure, which is subexponential or stretched exponential, if these conditions are satisfied. Okay, so here these conditions are slightly different from the previous conditions. You see, in the polynomial case, I had to assume that I knew the asymptotic behavior of the coefficients. I knew what the limit was. I knew what they were proportional to. Here, I can allow sort of oscillations, as long as the oscillations as x goes to infinity are not too wild. The oscillations are bounded, but there needn't be a limit necessarily. Okay, so this is somehow the point. So there is this b, and there's this sigma that satisfy this sort of these inequalities asymptotically for large x. I see now here I didn't write it, but yes, this is all sort of asymptotic. That's the only thing that matters. So there exists some constants alpha L and alpha U and beta L and beta U, such that this holds for all sufficiently large x in norm. And then I can do the same thing, right? Because people before us have looked at upper bounds. So now use the same sort of machinery, find psi, find phi. They look like this. Now this hyperparameter h that helps me control the tail of the marginal has to be not linear, but has to be exponential. Okay, and you get this matching bound. So this is this paper by Duke and Four and Willin from 2009. Okay, where they gave this upper bound, and you do the same analysis I described earlier. You get these lower bounds. You see, you note here we get exactly the same exponent. And now you may ask, and here also you actually get the rate for the total variation. And you may ask, okay, so where's this epsilon that I was talking about earlier, right? Because there was epsilon before, I need to do some perturbation. And the answer is, here you get exact exponent, but the epsilon is hiding in this constant here. Okay, the epsilon will be hiding in this constant because these constants are not the same. Okay, these constants are not the same. But okay, so now this tells me the rate of convergence in this stretched exponential situation. Right? Okay, and of course also these methods, well, of course I say of course, but these methods also work in the case when if p is equal to 0, but p and l are equal to 0 here, right? These are both the same. So here this is excluded because of this strict inequality here. But if this is the case, then this model is going to have exponential tails and it's going to be exponentially convergent. And we have lower bounds that are also exponential, right? So in other words, it is not, you know, it's not super exponential, right? It's not e to the minus x to some power greater than 1. It is not like that. So the rate is exactly of this type. Okay. So, and now I promised earlier a Levy-driven example, and this example is sort of motivated by Fortin Roberts. They noticed this phenomenon, you see. So we slightly generalized because they looked at the driver, which was compound Poisson, and there's really no need to do that, right? So this example is, I find it interesting because this Levy process, this Levy driver is sort of arbitrary. I only make really assumptions on large jumps. Okay, so let me explain first. So why did Fortin Roberts introduce this, right? So anybody who deals with this sort of convergence will tell you that if you have, drift like that, minus mu xt for some positive mu, that drift will drive the process back very fast because it's proportional to how far I am. The further I am, the more push I get. So you would expect geometric ergodicity. But in fact, if the jumps of the Levy process, the positive jumps of the Levy process, this is a toy example, so we just work on R, but this is not a restriction, definitely. But just to demonstrate the point, if the Levy process is very heavy-tailed, then geometric ergodicity will fail. Okay, it will, well, somehow indeed, because so these big jumps, you'll get strong push, but it will fail. And now the question is, so they demonstrated this fails in the compound Poisson case. Now, but enough, what is enough is the question, okay? So you see, if the Levy measure is for example, polynomial decays and positive jumps, this is not enough. You see, so this is a crazy tail of the Levy measure. You see, this Levy measure decays as 1 over log R to the MC. You see, so this is really very, very heavy. So only some logarithmic moment exists on the positive side. Okay, only some logarithmic moment exists, no polynomial moments. Okay, so if it's that heavy, and so all you need is the remainder of the Levy measure, the negative tail and the stuff that happens around 0 is not important. What you need to assume is, of course, that the negative jumps are not going to ruin you. Not going to change this phenomenon. And for this, what this means is that this negative tail just has to be less bad or less heavy than the positive tail. But the positive tail is so insanely heavy that almost anything you take will be like that. And the stuff around the origin, the small stuff, the hard stuff for the Levy process, this will not influence this intuitively, at least, because this is a martingale which has all moments, right? It's not going to inform, it shouldn't inform long-term behavior of the process. And this is indeed what happens, right? So you see, this process can be very skewed, right? It can be very, very skewed. But the behavior is as I will now describe, okay? So again, my functions v, sine, phi, and psi are here. And here I take this hyperparameter that controls the marginal. I do the same thing. And the blue bounds are Fortin-Roberts bounds, okay? So they showed that, you see, the tail here of the stationary measure of that process is even heavier than the Levy measure, okay? So the Levy measure was 1 over log R MC to the power MC. And this MC, I probably should have said, and I did indeed, that it is greater than 1. I assume that it's greater than 1. So I subtract this guy, okay? I have to subtract this. So this had very heavy upper bound. Okay. But in fact, this very heavy upper bound is really asymptotic, right? So up to this epsilon, because here again, I'm not, I don't know exactly what happens with the process around outside of the right tail, in fact, right? So there is, the process is not going to spend much time there because this Levy measure is going to shoot it up almost to infinity on the positive side, and it's going to somehow wiggle there and then eventually come back. And then these events are going to recur. So anyway, so the rate is good. And you see, even though the heaviness of the tail of the stationary distribution is logarithmic, the convergence is nevertheless polynomial, right? And in fact, Fortin-Roberts had a good rate, right? So their rate was MC minus 1, and we get a lower bound from these theorems that is exactly. Okay, good. So now maybe the last 10 minutes, I have 10 minutes. No, maybe I have what? Let's say 6 minutes, and then I ask some questions, okay? So I'll try to give you somehow how this works, right? So you see, I will not go into detail. So half of my presentation is in fact on the proof, but I'll give you somehow an overview of what happens, okay? So this is just a reminder of what these conditions looked like. This remark, and then I have here this theorem, I remind of the theorem, but let's not do that. Okay, so as I was saying, I mean, you're working with the general Markov process, so you don't have structure, you can't do coupling, right? Well, can't do, it's difficult, right? Because, you need some SDEs, people study convergence, but, you take Brownian motions and then you couple the Brownian motions, get some sort of nice thing. But if you don't have the structure, then you really have to go back to basics, right? And the stability for upper bounds is analyzed by this idea of Dublin to somehow decompose the trajectory, find a small set or a petite set, and decompose the trajectory. The process keeps coming back, it has to be recurrent. So you decompose the trajectory into these excursions and study the excursions separately. Okay, so this is what you need to do. Excursions from a petite set. Okay. And now, what is important is I take some bounded set. What is important is the return times. The return times to the bounded set, right? So that's somehow I start in my bounded set and then I wait a tiny amount of time delta, or maybe not so tiny, and then wait until I come back. Okay. So I want to know about properties of the law of this. This turns out to be extremely important. So what do we need to know? Actually, not just the law of this, but really, they call this modulated moments, right? But to me, this looks like, and indeed it is, an additive functional of the excursion of the process. So for an arbitrary non-decreasing function h, I need to understand something about the law of this kind of guy. See, if h if h is constant, then this is just this time, okay? Right. So how does the proof work? The proof is in 3 steps, okay? I start with my assumptions, these lower drift conditions. And what do I need to do? I need to understand a lower bound, a lower bound on the tail of this distribution, of the distribution of this additive function, okay? And then if I get a good lower bound there, then I can prove that every petite set is bounded. Okay, I understand that. I didn't tell you what a petite set is. I don't know if you know, but you know about small sets. So in Markov chain theory, right? So what you do is you want to somehow do some coupling, right? And to prove convergence. And what you do is you try to find the small set. So this is a set which is typically compact, such that when the process is in this set, the next step, no matter where you are in this set, is bounded uniformly from below by some non-trivial measure, okay, which is going to be a sub-probability measure of necessity, okay? So because it's bounded above by all the laws from all the starting points. And if you can do that, then when the processes are in there, they can sort of jump together with the same step with some positive probability. And then once they meet, once they've coalesced, then they will be together forever after that, okay? So this petite set is a generalization of that notion that works in continuous time, okay? So what we need in our proof is we need to sort of characterize all the petite sets. So in fact, we need to prove that under our assumptions, all petite sets are actually bounded, okay? Now, that's possible to do once you have this good lower bound on this probability. And then from there, when you have these 2 facts, you can then derive or conclude a lower bound on the tail of the distribution, okay? The tail of the distribution, so decay of the lower bound on how the tail decays, yes. Okay, and then once you have this lower bound tail decay, then you can soup up a little bit this idea of Martin-Heyer to get, because this is, so his idea was, so he looks at models in physics, of course, and he looks at some hypoelliptic diffusions, and he noticed that if you know the stationary measure of the system, then you can get a lower bound, right? But what he didn't have was he didn't know how to get a good lower bound on the stationary measure unless the system was built so that it has a given stationary measure, the sort of MCMC kind of situation, okay? So now our methods, our theory really provides this first step and then generalizes a little bit he of course didn't look at F variation, right? F variation is some sort of statistical kind of thing, right? But of course it all works once you have this lower bound, okay? So that's how these things work. Now, what else can I tell you that I can tell you in all this short amount of time? I wanted to do some of these arguments. but maybe not. Right. So maybe in order to conclude, okay, so there's some pictures here. You can ask me about how the proof works if you like. But if not, I should just tell you at the end. Okay, so the paper is out. You can find it on archive. And also I run a YouTube channel where I describe what I've just told you in short bits, some short videos. So you can look up. So for example, there's I recorded 2 videos, 15 minutes each, roughly. The first is what I told you, and the second is about the proof, right? So it's there, and you can just find it and enjoy it, hopefully. And if you have any questions, you can let me know now or later. It's all fine. Thank you very much.